Hello. I'm going to review a couple of concepts before we move forward to methods to estimate the time of concentration that we have also seen, and then a method to calculate peak discharges from a watershed. So remember, hyetograph is the time distribution of the rainfall. The intensity is the depth over time, and it's measured in inches per hour, millimeters per minute, or millimeters per hour. We mentioned in one of the previous videos that the intensity depends on the duration of the storm. So let's take a look at this figure and see what it's telling us. You have intensity in inches per hour versus duration. So what we see is that storms with lower duration are more intense. Longer duration are less intense. So then what we see is that whenever you have here the 2-year, 5-year, 10-year, 25-year, the higher the average frequency or the recurrence, the more intense the storm. That's the second thing. Again, the average frequency or the recurrence, as you increase the recurrence from 2 to 5 to 10 to 25, what you can see is that the intensity increases. The difference in intensity is less whenever you have storms of longer duration. So this distant difference here, for example, this is larger, and maybe here it is more dramatic. This is the difference, and then here you see the difference. So as you increase duration, you decrease intensity. As you increase frequency, you also increase intensity. Now, this is what we call an IDF curve, intensity, duration, frequency. You can find these curves as this graph shows, but also sometimes you find data. So you can find it as in a graphical form. You can find data that gives you the intensity for different durations of storms, or the third thing is equations. So you could find the equation that depicts this IDF curve. It's the intensity, duration, frequency curve. So whenever we look at this, this is the duration of the storm. So we're going to review time of concentration. Remember that we define the time of concentration from the beginning of runoff to the time at which the entire watershed is contributing to runoff that reaches the watershed outlet. That's the time of concentration. And remember that it's also the travel time from the hydraulically most remote point in a watershed to the outlet. So, to calculate the intensity of a designed storm, we need an IDF curve or data or equation, because you can see the IDF in different ways. So what we do is to determine the intensity of the design storm. For the design storm, we say that the duration of the storm equals the time of concentration. Now, in a way, it makes sense, because you know that the time of concentration is whenever the whole watershed is contributing to the outlet. If you have a longer time, still is the same, 100% of the outlet. It doesn't go beyond that. So is that clear? So time of concentration is different than the duration of the storm, but for design storms, we equal the duration of the storm to the time of concentration. So whenever we are going to design, what we say, okay, this is the duration of the storm, T sub D, so I'm going to say that I'm going to have a duration of the storm equal to the time of concentration. Remember that there's different ways of calculating the time of concentration. You have already practiced that. The important thing is that you have to make sure that you add all the components for the time of concentration that you need to add: sheet flow, concentrated flow, or open channel flow. This is an alternative procedure to calculating the time of concentration. So you calculate one time instead of 3 different times. So what we have is this equation that has the time of concentration equal to L, and L is the longest flow path in the watershed. And the units are super important here because you have the time of concentration is in hours, the length of the watershed is in feet, and then the average slope is expressed in percentage. Okay, so that's important. Then you have to calculate S, and the way to calculate S is by using what we call the curve number. So whenever the problem tells you calculate the time of concentration using the Soil Conservation Service method, the SCS method, is using what we call the runoff curve numbers. The runoff curve numbers, we'll see how we use it in other ways later, but for now what happens is that it takes into account the precedent moisture condition of the soil and also the type of soil. Goes from A to D. And we will see what that means in a moment, but the problem will tell you most times what hydrologic soil group it is, and then what is the land cover type, if it's urban, if it's residential, if it's agricultural, and so on and so forth. So that then this curve number would be, if it's commercial and business, soil type B, then it's 92, and that's what you will substitute here in the curve number, and it will give you a soil moisture storage deficit in inches. So then this here, that S is in inches. So the units are very important. The soil groups have to do with the permeability of the soil. So you have soil A, it's high infiltration, versus D, which is low infiltration. And then you have a gamut of soils between the two. Then the other thing that is important is the antecedent moisture condition, if it's low moisture or high moisture. Those two things are going to be very important, and you'll see later why. But for now, what you need to think of here is that this is the alternative procedure to calculate TC. So when a problem tells you use the SCS method to calculate the time of concentration, this is the method that you will use. So then, if you're in El Paso, this is another way of calculating the time of concentration. So we have seen now this is the third method to calculate the time of concentration. So it has to tell you, the problem will tell you which method to use. In El Paso, you would use the drainage manual, of course. And remember that I told you the IDF curves, you can find them in graphs, in tables, or in equations. And then in the drainage manual of El Paso, they give you the equation. So this is the recurrence interval here, 1, 2, 5, 10, 25 years, okay? And then you calculate the intensity based on the time of concentration. And then in the drainage manual, it tells you that the time of concentration you calculate in different ways depending on the waterway that you have. So if you have shallow concentrated flows, you use the Kirkpatrick formula, unconcentrated and concentrated flows. This is very similar to the same method that was presented in the class earlier, okay? What happens here is that here there's a little bit more of information. So for example, the Kirkpatrick formula, it's used for design of parking lots, for example, and you have to calculate, if you have concrete or asphalt surfaces, then you calculate the time of concentration using that equation, and then you have to multiply by a factor of 0.4. So this is a very common methodology to use. Okay? So the question is, what is the intensity for a 100-year, 24-hour storm in East El Paso? You're going to use the drainage manual. You can pause the video while you do that. Now we're going to calculate the peak flows for design of hydraulic structures. And this is whenever you don't have a gauge and you don't have historical data to say, well, this is the peak flow. So based on probability and statistical, they call it stochastic hydrology, they have developed these models to calculate peak flows. That's beyond the scope of this book, so we'll just show you the methods that were developed to calculate peak flows. So the oldest and most widely used method is called the rational method. So the rational method is used to size hydraulic structures such as drainage inlet, storm sewers, drainage channels, and culverts. So it's very commonly used. This is the rational method. The equation you should remember, QP equals CIA, where C is the runoff coefficient, I is the rainfall intensity of duration TC. Okay, remember that we have the duration of the storm equal to the time of concentration. The units are very important as well. The area is in acres. So, that's what I just said. So the runoff coefficient. Now remember, whenever you did the rainwater harvesting study, you did not get 100% of the rain that fell on the little roof of your little house. So what happens is that there's some inefficiencies in that runoff, and the runoff, if you have concrete or lots, the runoff coefficient is very close to 1, meaning that not much is lost. But if you have parks or lawn, for example, a lot of the water or the precipitation will be trapped and also will be slowed down. So that's why then you have runoff coefficients that are 0.1 to 0.2, meaning that some of it is lost. Some of that flow is lost. And lost is probably not the best word, because that doesn't mean it's lost, but it goes somewhere else. It doesn't turn into runoff. So if you go to the El Paso Drainage Manual, again, it gives you some runoff calculations. One thing that we'll do is whenever you have compound sections, let's say that you have different types of land cover, you have to calculate an average weighted runoff coefficient, which would be the coefficient for that specific area times the area. So you do a summation divided by the area. And we'll do one of those problems later. But for now, just remember that if you only have one type of land cover, it's only one value of runoff coefficient in one area. But if you have a combination, this is what you'll have to do. So I want you to work on this problem. You can pause the video. You'll have a copy of that, and you need to turn in one per group. So for the following example, I've shown an IDF curve in figure 11.26, which is what you already have, and it's in the book as well. The hydraulic length is 4,500 feet. The soil type is C. And there is a 250-acre watershed whose predominant land use is horse pasture, with an average land slope of 8%. The question is, what is the 10-year peak discharge? Then the land cover uses change to single-family residential, half-acre lots. What is the 10-year peak discharge after development? I will give you a few minutes to try and identify what you have to do. You can pause this video, and I will solve it when you come back. If not, We can do it right now. So the first thing is to determine the time of concentration. Remember, we're using the rational method, and the rational method is QP equals CIA, right? We have to determine the intensity, and to determine the intensity, you need to calculate the time of concentration. We'll say this is the duration of the storm. You need to calculate the coefficient, and the area is given. But in order to determine the time of concentration, we're using the alternate method. And so in the pre-development, it tells me that it was horse pasture, clay loam, with an average slope of 8%. So I need to determine the curve number first to calculate that storage deficit. And so it's it also told me that it was clay hydraulic soil C, and so it's pasture, so it's 74, and this 74 is what I have used here. And then this storage deficit is in inches. This number I'm going to substitute here. The length was given as 4,500, and it's in feet, remember. And then the y, which is the slope, is in percentage, so it's an 8. You have to be very careful with this. And then the result of this is in hours, and you need to convert it to minutes. Remember that you can look at this, and if you don't understand something, you can stop or go back to the explanation. So the coefficient, the runoff coefficient. So pre-development, we said that the land use is horse pasture. So the definition is kind of different. If you look at here, is horse pasture, and it also says clay loam, but there's no clay loam in this. But then here I have the clay soil. Okay, so we can use any value between 0.45 and 0.55. Let's use 0.45. And then after development is a single family residential half-acre lots. So here we can use a value of 0.35. In the exam it would be more clear. Now, depending on what you're using it for, that's the value that you use. Remember that if the runoff coefficient is larger, that means that you have a higher percentage of runoff. So whenever you're designing a hydraulic structure where you have a high risk of human loss of life, then you would like to have a runoff coefficient that is higher, because that means that you have more runoff. If not, you go lower. So that's why I went here lower, and then here a little higher than 0.30, and then here 0.45. But you know, you won't have to make those decisions at this point. I should give you those values. If not, just use an average. So as I said, what you do is that you calculate the time of concentration. So you have to follow this same procedure and calculate the time of concentration for the residential homes, and it's here, and so it's half an acre home, soil type C. So you substitute the 80, you get 2.5 inches, that goes here. This is 8%. This is given in hours, so now I have 37.4 minutes. Okay, so what we have here is for pre-development, I have a time of concentration of 45 minutes, and then for post-development, I have a time of concentration of 37.4 minutes. So in the problem it tells me that I'm using this curve, and it's a 10-year storm, So I put the time of concentration equal to the time of the duration of the storm and obtain the intensity in inches per hour. So this is what I obtained. It was 2 inches per hour for the pre-development. It's 250 acres and the coefficient was 0.35, and the answer is in cubic feet per second. It's a peak flow. And then for post-development, this is my coefficient of runoff, my intensity, and the area, and it's 349 cubic feet per second. So now you have two problems to solve. Here is the peak discharge. This is straightforward. Practice that. In this one, it will require you to do a little more of calculation, in the sense that you have 52 lots of 0.06 square kilometers, and then you have the home, so you need to do a sketch to solve this. So make sure that you correctly do a sketch of this subdivision that we have, so that you know exactly how to calculate that compound coefficient of runoff, like I mentioned at the beginning. So good luck.